everyone to another edition of the Connexus webinar series. Today we are talking about PHA for Engineered Safeguard Definition. Our presenter today will be Gary Carithers. And I'll go ahead and allow Gary to tell us a little bit about himself.
Thank you, Matthew. Good afternoon, everyone. I appreciate you joining the webinar. My background is quite extensive. I've worked a number of years, over 20 years, in the process safety and risk management end of the business. I started as a process chemical engineer and worked in various functions from technologist to engineering and production management, and in the later years primarily as a hazard and risk analyst. So I can tell you I've been a process hazard analysis. I've been on both sides of the table. And I can tell you, it's tough to hold all these different hats, but it gives me a different perspective about the business. I can tell you, we're here to talk today about the process hazard analysis, commonly referred to as a PHA, as it pertains to engineering safeguard definition. So this is the product we seek to develop, a safety instrumented function list. All the functions that you want to analyze, got the inputs and the actions acquired, and it's done on a hazard by hazard basis. This is a key issue because first we have to find the hazards, which needs to be integrated to some acceptable level of risk. And that's the focus for Civinar. The result of a safety instrumented function definition is a SIF list. And a SIF list is a compilation of all the functions that must be implemented in an overall safety instrumented system to protect the process. Now, if we look at this flow diagram, the PHA is pretty much a qualitative analysis of process hazards, and usually done by a multidisciplinary team. Not a new concept at all. It's been around for more than 20 years, and it was put in place around 1992 because of OSHA regulation. And it caused the PHA to become much more prevalent in the industry. But the PHA methodologies were developed and implemented far earlier. And the inputs to this step of the safety life cycle, the safety life cycle that Kevin presented in several other webinars, the inputs include the process safety information such as PFDs and PNIDs, and other documentation that would be required to analyze potential deviations from the normal intention or deviation of a process. And the PHA involves analyzing those deviations from the design intent all the way up to what might happen to give you a credible hazard. And if you find consequences, after those consequences are identified, safeguards are in place to prevent those hazards from reoccurring. So a qualitative assessment of the risk is made by the PHA team somewhere along the line. They use risk guidelines made from the operating company typically, and most of the time they use a risk matrix. And if the safeguards aren't adequate, then the team makes recommendations for reducing or eliminating whatever hazard they found. And some of those recommendations might be to add a safety instrumented function. So the result of this step, PHA analysis, is a report that identifies all the process hazards, and many of the safeguards that were identified to prevent the hazards during the PHA might also be IPLs that will be used to analyze in later analyses with LOPA to give you your safety instrumented function SIL level. Okay. So the definition of a safety instrumented function is a very critical step in the SIS system safety life cycle, and it's the source of many design errors and common misconceptions about what constitutes a safety instrumented function. Now, if you look at a broader perspective, how does the PHA fit into the process safety management process? Well, to understand how the safety instrument system fits into the big picture, it's vitally important to understand how the hazards are identified and a management system which produces the input data for the SIS design. So a process safety management implementation system might be used to provide a framework for site process safety, to report incidents and near misses, and most companies use it to globally improve the consistency between the businesses and the regions. And if they get any new businesses, they also use these strategies to integrate those new businesses. But our bottom line, the key here, is to establish proactive identification and prevention strategy for process safety incidents. Next slide I'm going to show you is a pretty busy slide. We're going to go into each and every element in great detail. No, we're not going to do that. I just put this up to show you there's a lot of different process safety management systems out there. But process safety management is a management system. So how does a PHA, a risk assessment, a skill selection integrate into this PSM process? Well, an effective process safety management process requires a systematic approach to evaluating the whole process. And using this approach, the process design, the technology, operational maintenance activities, procedures, emergency preparedness plans and procedures, the training programs, all these elements work together, and it impacts the processes, and they're all considered as a whole. So the process safety management is the proactive identification and the evaluation or mitigation to prevent these chemical releases that could result from the failure of a process or as a result in a procedure or equipment. So it's quite pervasive. In the United States, the companies must comply with OSHA 29 CFR 1910-119 for their PSM management for the toxic and listed chemicals. But as you can see, APR 750 and the CCS, the American Institute of Chemical Engineers Center for Chemical Process Safety, also has a process that's very similar to OSHA PSM. Process hazard analysis. Now, I didn't say HAZOP or any particular method. Most PSM processes are performance standards in that you do what is necessary and sufficient to achieve that objective, and in this case, it's acceptable risk. So the PHA, if you're going to do an OSHA quality PHA for a regulated process, it would have to look at the hazards of the process, and you would also want to identify any previous instance so you could work that over and make sure you didn't have that kind of problem again or in your existing in your process. Ask you to look at engineering and administrative controls, consequences, siting, human factors, and to evaluate a qualitative evaluation, keyword there, qualitative, of the range of possible safety and health effects in failure of the controls on the employees in the workplace. This is a big job for a PHA. Be quite honest, the HAZOP is the workhorse of the industry, and will cover most of these potential issues or topical areas. Typically, after a HAZOP, most folks will do a siting and a human factors checklist just to make sure they cover their bases in detail. But what kind of formal techniques are out there? Well, OSHA says that this is a list you can use. And it gives you this half a dozen what-if checklists, HAZOP, FEMA, fault tree, or an appropriate equivalent methodology, which would be kind of hard to come up with one that would be more specific than these. But the size and complexity of the process influences the decision as to the appropriate methodology to use. All the PHA methodologies are subject to certain limitations. For example, the checklist methodology works very well when the process is stable, no changes, but it's not as effective when the process has undergone an extensive change. So you'd miss the most recent changes and they wouldn't be evaluated. So the PHA is dependent on very good judgment, the assumptions made during the study, which need to be documented and understood by the team, and then the PHA is kept for future PHAs for further evaluation. So several of the techniques are more appropriate used for performing general process hazard studies, usually early during the life of process, such as the safety review, the checklist analysis, the relative ranking, PHA and what if. They're efficient at taking a very, you might say, a broad brush look at the inherent hazards of a large plant or complex process. The other hazard evaluation techniques, such as the what-if checklist analysis, the HAZOP, and the FEMA, are excellent choices for performing a detailed analysis of a wide range of hazards during the design phase and during routine operation. So A lot of times these studies will be followed up by more sophisticated techniques such as fault trees. We'll give a little bit more detail on those in a minute, okay? What are the other support methodologies I had in mind and use routinely? Well, LOPA. LOPA is a flexible methodology that quantitatively estimates the likelihood a hazardous scenario occurs. It's easier to use than a fault tree, and it complements a HAZOP very well. LOPA is used to assess the risk, is intended to be used after a screening study, not before, but after. A screening study such as a HAZOP has identified the hazards that should be subject to LOPA-type analysis. So LOPA takes into account all the existing layers of protection which are available to bring the process to a safe state, and then it assigns a probability of failure demand to each layer, which gives you a much better estimate of likelihood than the purely qualitative estimate from a PHA. I'll talk about the other studies in a minute. But we have compatibility matrix, we've got relative ranking, got reactivity studies, consequence modeling, and inherently safe design studies. And then last but not least, QRA. Okay? We're going to touch base on these very quickly. Reactivity matrix, some people call these a compatibility matrix. And you can see this is a whole lot of information. Well, what do you do with it? Well, most of the time it's used during a HAZOP or some process hazard analysis when you're talking about various things to determine if there's a compatibility issues, if there are reactivity issues involved with various chemicals when they use them. And most of the time you just construct one with an X and Y axis. You populate the components on both axes, and then you look at what the results from inadvertent mixing might be. Where do you find data like this? Well, one place you can find it is NOAA, National Oceanographic and Atmospheric Administration. You can go right on there and create a number of different matrices with various chemicals that you wish to react with. Now, also you should include materials of construction, whether it be stainless, carbon steel, elastomers that you might have in your process that you want to see how the impact that wetted contact might be with your material construction and your chemicals. Okay. Inherently safer design strategies checklist. Now, keep in mind, chemicals by their very nature may be hazardous. The hazard's intrinsic to the material. Chlorine's toxic ventilation. Sulfuric acid very corrosive to skin. Ethylene's very flammable. Acrylic acid could polymerize or release large amounts of heat, or any monomer. Steam confined in a drum at 600 psig contains a significant amount of potential energy. So you can't change an intrinsic property of a chemical, but you can use these strategies to reduce risk. We talked about minimizing the quantity, and you put in a safer chemical for a more hazardous chemical. Can you moderate the process? Can you use less temperature and pressure rather than a higher temperature and pressure? Can you design the facility more simply so that operators will be less likely to make operational errors? Okay? So these are common sense strategies, but you actually can employ checklists to look at these in greater detail. CCPS has put out a little yellow book, can't think of the name of the subject right now, but it's just on inherently safe design. A very good book. One thing before I launch into PHAs, I want to talk a little bit more about process safety information, because it is the cornerstone of PHA studies and also safety instrumented system design. PSI is a regulatory requirement under OSHA PSM, and I'll show you the different types of information we're talking about that we might be needed for a PHA, but it's a process develops from a conceptual design stage to a more detailed design stage. Process safety information also develops, becomes more sophisticated, and as such, that more rigorous PHAs can be conducted. Okay? When we talk about what would be the information pertaining to the hazards of a highly hazardous chemical, well, you're talking primarily about the toxicity information, the corrosivity, the reactivity, the physical characteristics. A lot of this information can be, see if I can establish a pointer. A lot of this information can be used can be found in the material safety data sheets. And a good practice for a HAZOP or any PHA, if they've got specific chemicals, aren't necessarily hydrocarbons, although those are you can review, but I'm talking about specialty chemicals in particular. Go over the hazardous chemical MSDS with the entire PHA team before you start so that they can understand the kind of issues we'll be addressing, the reactivity, chemical stability, flash point, things of that nature. Okay? Information pertaining to the technology of the process. What are we talking about here? Process chemistry, inventories. Does it make a difference whether you spill 1,000 gallons or 100,000 gallons? Of course it does. If we're going to study and make a study of these processes and we want an accurate assessment, we need to know the volumes and types. Safe upper and lower limits for such items such as temperature, pressure, flow, composition. These parameters are needed to do a quality HAZOP, and they're also needed for development of safety instrumented functions. Okay? And then information pertaining to the equipment in the process. What are we talking about here? Well, material construction, P&IDs, electrical classifications, ventilation system design, material and energy balances for the systems. What kind of safety systems are in place already? The relief system design and design basis. If you're going to give a relief valve credit as an independent protection layer in a LOPA, then you need to know whether the design basis of the relief valve, whether it's really acceptable for it to be an IPL. Okay? A topic of another subject later on. Brainstorming technique. Had a little brainstorm right there. There's a number of different techniques we're going to chat about here. Safety reviews, preliminary hazard analysis, what if, and these are relatively unstructured, obviously, as I've denoted here. And then you've got some stuff that's more structured, the HAZOPs and the FEMAs. First, I'd like to talk about the safety review. It was probably the first hazard evaluation method ever used. It's intended to identify plant conditions or operating procedures that could lead to an incident and result in injuries or property damage or environmental issues. Typically, plant's already ongoing when you have these things, and it focuses on the major risk situation. So safety reviews can be used to ensure that the plant and the operating and maintenance practices matches the design intent and the construction standards that the plant was designed to. Okay. Preliminary hazard analysis. In fact, I conducted a preliminary hazard analysis a couple of weeks ago. The PHA focuses really on a general way on a hazardous materials in the major process areas of a plant, and it's conducted early in the development of a process where there's not as much information on design details or operating procedures. So it really formulates a list of hazards and a generic hazardous situations by considering things such as the facility layout, plant equipment, raw materials, the operating environment, operational activities, testing, maintenance, things like that. And so it usually takes, you usually have one or two people, one or more analysts to assess the significance of these process hazards, and you may assign a criticality ranking of prioritize or recommendations that comes from this type of process, but it's used early in the design, before a HAZOP primarily, and after the design has a good conceptual basis. A what-if analysis, and it's really a brainstorming approach in which a group of experienced people familiar with the process, they ask each other questions and voice concerns about possible undesirable events that might occur in a process. Not very structured, but it is carried out in the industry at almost every stage of the life cycle of a plant. Talk about that a little bit more in a minute. So the what-if analysis encourages the hazard evaluation team to think about questions that begin with what if. What if I had the wrong material? What if the pump stops? What if a lightning storm comes over? Literally anything you can think of that's applicable to the process is available to ask in a what-if checklist. So typically questions are divided into specific areas of investigation like electrical safety or fire protection or personnel safety, and then we just ask questions by a team and you step through the process. So it's a powerful procedure if the staff is experienced. Otherwise, the results are going to be likely to be very incomplete. But it can be used at any of the stage of the life cycle of the plant. A what-if checklist analysis combines the creative brainstorming features of the what-if method with the systematic features of a checklist analysis. For example, the checklist analysis is an experience-based technique, and the quality of the hazard evaluation study performed is highly dependent on the experience of the checklist authors, okay? So if the checklist is not complete, then the analysis is not likely to address the hazardous situation. Now, conversely, if you add the what-if portion, then the checklist portion tends to give you a more systematic way to explore the what-if analysis, so it's a good hybrid technique that combines the creative brainstorming features of the what-if with the documentation capabilities of the what-if checklist, okay? And it's used during many phases of the plant life cycle. If you look at failure mode and effect analysis, I neglected to mention that, but a failure mode and effects analysis is usually used to identify a single piece of equipment and system failure modes of each of the modes and how it impacts the system or plant. And this analysis typically generates recommendations for increasing the equipment reliability, and which will improve the process safety of the plant. FEMAs can be done by a single analyst. We're not going to talk too much about that during this study. The HAZOP technique was developed to evaluate and identify safety hazards in a process plant and to identify operational problems which, although not necessarily hazardous, could compromise the plant's ability to achieve design productivity. Most HAZOPs I do, typically people will find a lot of recommendation to improve quality and yield and operational capabilities, reduce downtime. May not be a safety issue, but a lot of times HAZOP are money makers. But the main reason that we want to look at HAZOP is how it determines it's just a great technique, structured technique for determining the hazards that are in a process which we can accumulate and view later and determine whether safety instrumented functions are necessary. Works on continuous, works on batch processes. Now the HAZOP analysis technique does require up-to-date PNIDs and operating procedures and things of that nature. And it does require considerable knowledge of the process, the instrumentation, the operation. So you've got to have a number of these experts that know the process well in a HAZOP. Now, if you talk more about the applicability of the various techniques in a minute, but I wanted to show you how they're distributed over the typical life cycle of a plant. If you can look and see the safety review, which you've been reviewing for a minute or so here, safety review is used early in the plant, or it's not used very early in the plant. You don't have a lot of anything on paper, so it's kind of hard to just brainstorm a conceptual design. But it's used a lot later in the phases of the plant, everywhere from construction cleanup to demolition. A preliminary hazard analysis, once you have a conceptual design, very powerful on the front end of the plant. Checklist is used throughout. A HAZOP is used, in many phases of plant operation. Okay. So, I want to talk about the risk ranking technique, because it's really more of a strategy than it is the technique. It's the kind of thing you do early in the game so that you don't have to talk about it in a HAZOP really. But it's a general category, includes a large number of techniques, and you evaluate the properties of chemicals and use various multipliers to be able to prioritize a whole list of chemicals you have in a process. And so the main thing that you want to take from this is that it's used as part of a site review process. The Dow Fire and Explosion Index is a key example. designed for flammable, combustible, and reactive materials. And you can look at different processes of a plant, separate the units, and then you can apply these different factors, and you compare the scores from one area of the plant to another area of the plant, and actually determine indices for which are priority or high hazardous chemicals. And it also gives you a basis on how to choose where to start your PHAs. Used early in the process. Enough said. Checklist. We've talked quite a bit about checklists already, but so I'm not going to belabor the point. But use a lot of different checklists, particularly in concert with a HAZOP. They may be compressors, pumps, tanks, piping, loading and unloading systems. A lot of times vendors have a checklist based on their equipment that you might want to cover. When we talk about, I want to talk about fault trees a little bit. We use a lot of fault trees. It's usually used after a PHA has identified the very hazardous or complex issues. A very flexible and powerful method for modeling the failure characteristics of these complex systems. So the purpose of a fault propagation model is to estimate the failure characteristics of a system based on the individual components of the system and how they're related to each other, logically related to each other. And of the fault propagation models that are commonly out there, fault trees are particularly useful for analyzing failure frequencies of process plant systems due to really its flexibility and its accuracy and incredibly good documentation characteristics. So fault tree can model virtually any plant process failure scenario, and it's also capable of modeling some scenario that's not possible with other models, such as systems where both the equipment failures and the human failures are important, or that the overall system requires component failures to occur in a certain sequence. It's about the only tool that does a really good job of evaluating that complexity. Event tree is very similar, but it's well suited for analyzing complex processes. It's got several layers of systems that have several layers of systems or emergency procedures in place to respond to specific initiating events. So event trees are used to identify really various accidents that can occur in a complex process. After these individual accident scenarios are identified, then usually you understand the specific combinations of the failures, and you can use them later to determine the frequency with a fault tree. Okay, let's explore this in a little bit more detail. I said PHA studies are deployed throughout the life cycle of the process, depending on the need, and they vary in complexity and depth. Now, so you got an early crude analysis on some P&IDs, maybe that's all you've got, and then you've got a full study into detailed design. You could have a mini study on design changes, a pre-commissioning study for the plant, post-startup or revalidation study after the plant's been up and running. So PHAs depend upon concise and accurate process safety information while you conduct the study, okay? And so this is developed somewhat concurrently as a process develops, and I'm going to show you how this works a little bit. There's essentially two methods that are used to identify areas where safety instrumented functions are required to reduce the risk in the process. The first is through process experience. Most processes are not new, they rarely are started from a blank slate, okay? Process design is, in many cases, is based on proven technology that's been used over the years. And these are often process design templates from licensors that have safety instrumented functions already identified and key safeguards and hazards already identified. Then the process plants also have a large amount of information about common pieces of process equipment that might require safeguarding through safety instrumented systems, such as pumps, compressors, fired equipment, and of course it's designed and safeguarded in really in accordance with specific standards such as NFPA or API recommended practices for fired equipment or compressors, rotating equipment, that kind of stuff. But that's a reactive approach to risk reduction. It's incorporated into new unit design. Each time a new unit is designed, the engineering firm starts with a design template, so the risk reduction measures have already been accumulated over that part of the plant, the life cycle of that process. So this standard design information is really kind of shown as an offset here from previous processes. And the other method of finding hazard that require risk reduction is a proactive study called a PHA. Let's talk more about these PHAs. If you look early in the process, if you look at a chemical process life cycle, it goes from R&D through conceptual design, detail engineering, construction, startup, and routine operation. Early in the game, you don't have much to work with. You've got some basic chemistry, maybe a description. You look at process safety information, you've got maybe some prior design experience. So what kind of reviews can you do? Well, you begin starting checklists. You can start compatibility matrices. You can conduct some EHS reviews to get you a little bit more information. But as the information moves from R&D to conceptual design, you start to put together some really quite interesting parameters that you can use to do some study. Got most of your sizing is done now, material energy balances, raw materials are known, you've got some generic block flow diagram. So now you can do siting and consequence analyses on major hazardous and toxic raw materials to see what their impact might be on the plant or neighbors if a release might occur. You can also do some basic checklists, okay? As you move on to detail engineering design, you've got a lot of information available. P&IDs are in pretty good shape. You know what the vent design basis looks like, got electrical classification, the site layout, you've got control system and safety instrumented system design pretty much in mind. So you can do, top of the line HAZOP, and you follow up with LOPA or fault tree for the incredibly important areas that you've identified that require further analysis. And you can do some very powerful reviews at this point, very sophisticated reviews. Move on down the line a little bit. Plant's up and running. This is where you're doing some revalidation PHAs at this point. Probably already done one PHA or HAZOP. Now you're looking at revalidation. This is an incredibly important phase because it includes all the significant management of change reviews and audits, near misses, incident reports, prior PHA recommendations, resolutions, and there's a number of reasons why today's understanding of the hazards associated with the process might differ from an understanding that existed when the prior PHA was conducted. You've got new knowledge, okay? Process changes that have occurred that have introduced new hazard or accentuated the existing hazards. You've got changes in on-site or off-site occupancy, perhaps. You've got process changes that have happened over time. You also have, unfortunately, you usually have actual incidents that's revealed the scenarios that weren't previously identified in the previous PHA. You also have safeguards that you didn't know you had that maybe weren't credited when the first PHA were done. You also have changes in your safety instrumented system. It's also possible positive changes might have happened where you could maybe find some additional safeguards you didn't identify. So the point is, the safety instrumented function may be added or changed at any of the life cycle changes of the plant. So the SIF requires management and maintenance during the entire process. The safety instrumented system must be managed to meet IS-84 life cycle requirements as well as the PSM process. So therefore, it's necessary to integrate the IS-84 life cycle requirements into the PSM process because it draws information from the PSM process on a dynamic and ever-changing basis. And any of the SIF changes must be reviewed as to how the changes impact all the other PSM elements. This was considered when the IS-84 standard was developed. Now, the IS-84 life cycle, Kevin Mitchell talked about that in previous webinars, and that's key to this understanding that I've just talked about. So if you haven't reviewed that, please do so. Let's talk a little bit more specifically about the analysis techniques. Okay, what-if analysis, we've already talked about that in more detail. It's a what-if analysis. What if this happens, that happens. So very loose structure, and the questioning can be all over the place. It's a little bit hard to facilitate, but usually you get some pretty good results from it. It's an excellent technique for just reviewing the changes in a plant, okay, existing facility. Also good for pre-startup. Go in and ask a lot of questions. You've got operators in attendance, the plant's already running, so they know a lot about it, okay. Users need to be very experienced when you're talking about this type of a process. So, easy to use. Flip side, disadvantages, it's hard to achieve quality control big time. Results are highly dependent on the experience and thoroughness of the leader, and to a certain extent the group. Okay. So let's talk about HAZOP a little bit, because HAZOP's the workhorse of the industry. Remember, it's used to evaluate the design and operation of hazardous process facilities. It's about the only good technique I know of that does both of these operations, the design and operation, because that's where the design marries to the procedures and how operators really run the plant. So HAZOP typically identifies deviations, looks at the causes of those deviations, recommends actions, and records recommendations. It's well-defined scope usually, because you're talking about specific nodes, and you step through the whole process with well-defined nodes. Takes good leadership for HAZOP. It's used in almost any phase of the process, and guide words help identify the deviations beyond the safe operating limits. And the deviations are typically caused by normal control equipment failures, human errors, misoperation of equipment, failure of pumps, compressors, motors, shutdown valves. For each credible deviation from the normal process control, a credible cause and a potential consequence of that deviation is reported. So a fundamental assumption is when a process is operating in its design envelope, the potential for the hazard and operability problem does not exist. So as we can see, the process safety information is very critical for making sure that you understand your process and the parameters that you are HAZOPing against, okay? Now, obviously, it's a very effective process. The disadvantage is it's much more complex. You've got to have a pretty good team, and it takes a little bit more time, but it's the best thing going. Okay, after you get done with your PHAs, most of the time you're going to develop some recommendations, or you may have causes that might be difficult to respond to. You've got consequences, you've got safeguards, and the team's trying to agree. Okay. Sometimes it can be very difficult. But sometimes you just say, hey, let's shelve this, or move the recommendations aside for further study. Recommendation to get a better study, where you've got a better understanding, and move on. Okay, don't try to solve problems in the HAZOP. Hard to do, but nevertheless, that's the cardinal rule. Okay, and also if they become causes become very complex, it's like beating a dead horse. You know, you just have to move on. So you may want to recommend that it goes to a LOPA or a failure mode and effects analysis or some other study if you can't resolve it in the HAZOP. Okay. Good way to characterize recommendations is to use a risk matrix. And I'm going to show you this risk matrix. Obviously, the stuff in the red and the magenta and black, that's all really bad stuff. Okay. So this is a risk matrix. It's used in safety instrumented system engineering to make decisions, and also in the HAZOPs make decisions on the number of layers of protection required for a specific hazard. And it's related to its consequence, severity, and likelihood. So, for instance, if I had a very high consequence that might cause a single fatality might be a 4 in terms of severity, and it may happen not expected, maybe once every 10 years, or would be a high frequency rate. But if you wind up in the severity times the likelihood, if you wind up in the red zone, very bad. Requires a number, at least 3 IPLs to achieve a tolerable level of risk. So the matrices tell us the order of magnitude of risk reduction based on the likelihood and the consequences. So to move down, to move over 2 blocks would essentially be the same thing as saying, I'd need a couple of IPLs to achieve that level of risk reduction. These descriptions reflect action levels required relative to the residual risk of the process. That is, the risk as to the initiating frequency and a probability of failure of demand on the independent layers have been applied. So these are the groups to see where they stand. Read over your recommendations, fine-tune them, and then put them in the front of the report. The key issue here, Trevor Pletz is a giant of process safety arena and had a number of different books. And he had one comment I remember that he summarized the HAZOP as provide a final check on basically sound process design to make sure that none unforeseen effects have been overlooked. Okay? Now PHAs have quite a few limitations. They're not intended to address non-process hazards and higher level issues that require a QRA, such as dispersion gas cloud analysis or other kind of things. That should be done at a different study. Okay? Not necessarily done in a HAZOP. HAZOP doesn't consider double jeopardy events. That's 2 or more failures that might occur that are self-revealing, and those are very likely to happen at the same time. The limitation really on the process hazard analysis is the team members, part and facilitation, and also the expertise of the team. And process safety information, let's face it, if you don't have good information, garbage in, garbage out, your PHA will not be a quality PHA and will lead you to conclusions that you want to achieve. So a process undergoing a pre-commissioning study on an as-built plant should be sound with regard to the scope and procedures. Common problems with PHAs, what might they be? Well, they kind of characterize these in terms of inadequate. You don't have a skilled facilitator. You don't have good process safety information. You don't have good up-to-date operating procedures. Or PHAs that don't do a good job of documenting what we've talked about in the study. The recommendations are vague, or you don't even know what kind of review it is or how it was analyzed. Okay. A lot of times there's a lot of things that people fail to do. Document all the credible hazards. Cover all initiating events. Cover all the different operating modes, which is required by PSM for regulated processes. They don't talk about, a lot of times, ancillary processes, utility cleaning, abatement systems. They don't detail the nodes very well, so it's hard to tell what's covered. They don't carry the consequences to a global conclusion. If I've got on this node I'm talking about a pressure event, it may have upstream or downstream effects. Those need to be denoted. They don't consistently rank the scenarios. They don't cover past incidents. Okay? And then this is where you really give too much credit where it's not deserved. Extra claiming. Claim extra safeguards or conditional modifiers. In other words, people really around all the time, and you may say, well, they're not around very much, so you may add a factor of 10 in there to compensate. Ineffective safeguards. An operator may respond to a temperature alarm and have some task, but he's got 6 seconds to do it when it takes him 15 minutes to analyze and respond to that. You don't take credit for those kind of things. Or excessive optimism in what might happen if you had a consequence. Okay? So a HAZOP isn't an infallible method. It's not a good substitute for design. HAZOP team is very critical. when you look at modifications on the existing plant, you have to very, very extensively study the management of change that's been done so that you can understand the changes and reach a proper study based on the potential new hazards that might be introduced. And the HAZOP can't predict deliberate acts of sabotage. So if you've got that kind of an issue, you really should consider doing a security vulnerability analysis to identify the concerns and address the issues with appropriate strategies that are outside the venue of a HAZOP. HAZOP, things like utility shutdowns, things of this nature should be viewed in a separate, in a major hazard review. It's probably not the right place in a HAZOP. Identify your critical equipment and controls, analyze them carefully, provide any redundancy efforts if required. And you always want to make darn sure you study the unit startup and shutdown cases, because a normal run is a whole different scenario. You may just discover some interlocks that are bypassed in order to start up and how those can be handled or forgotten, and then what kind of repercussions might happen. And operator response in an abnormal or emergency situation should be identified and tested and verified. Okay, these are different studies. HAZOP may not be the best for those. Okay, so the major perspective management must support and act on HAZOP recommendations. Many of the recommendations made with a lot of effort by the team are forgotten just due to lack of follow-up action and no support from their management. So, real bottom line, the success of a HAZOP depends on the building experience of the study leader and the team, and it depends on the process safety information and the materials that you have to analyze. They need to be accurate. So that's pretty much it for the PHA overviews, and you can see that safety instrumented functions accrue during the entire life cycle of the plant, and will more likely accrue when you get into the HAZOP, faultries, and some of the more sophisticated techniques, because they can delineate the independent protection layers that are available to circumvent a problem, and then accurately determine whether the risk is acceptable. So our objective is to meet acceptable risk with the safety instrumented functions. Thank you very much.